Hello everyone, and we are back, and we're talking about area under a curve. And last lesson we talked about how to evaluate the exact area. So let's recall that. And I left you at, and you were probably like, huh, you didn't go over how to use a calculator. Exactly, because that's what this video is meant for. All right, so recall that if we have a function and arbitrary function f of x, and we want to find the exact area under the curve from a to b. To get the exact area, we would use two things. We would have used the Riemann sum that we know how to do, which is from 0 up to n minus 1. So for a random amount of rectangles, for n rectangles. So this is n rectangles on the interval a to b. And then we have the width of every rectangle times the height of every rectangle as follows. And then what allows us to get the exact area isn't just using the Riemann sum, but it's using our knowledge of limits to make the number of rectangles approach an infinite amount of rectangles. So we approach an infinite amount of rectangles, then the area of the error that we're going to get is so marginal that we're going to say it's the exact area. All right? And then what we learned last video is that this is the equivalent of writing the integral from a to b of the curve f of x, which will represent the heights of the curve, dx, which represents the width. So that's what we did last video. We talked about the integral representing the exact area and where it comes from with the Riemann sums and limits. Okay. Now, we looked at an example. So in 4.1.1, we looked at an example y equals x plus 4, which looks something like this. And we calculated from -2 to 3 of x plus 4 dx. And the way we got this area was using a trapezoid. Right? And that's great. However, there's not infinite amount of shapes, and function can be all sorts of things. So what if, for example, we had the function f of x equals, just say x squared, and we want to evaluate the integral from 0 to 4. So if I make a sketch here to help you visualize this, there's your curve f of x. 0 to 4, obviously I messed up on my curve, but if I scaled by halves, 0 to 4 would be a section like that. Well, because there's a curve there, there's no shape that gives us the exact area. And you could try and use the idea of Riemann sum. So you could try and do the limit as n approaches infinity of 0 to n minus 1 of, it would be 4 over n, f of 0 plus 4 over n x. And you could try and do this, but the problem with this is on a graphing calculator, there's no such thing as a limit on a graphing calculator. All right? Limits, there's no button for a limit on a graphing calculator. Okay. So with the way we do this is we don't actually use this definition, we use the integral. Well, the integral is programmed to represent this, so don't feel like it's a different button. But we're going to use the integral from 0 to 4 of x plus 4 dx. And this calculators have. We don't have limits, but we do have the integral on a calculator. So where you find that at is you go to math, and if you keep scrolling down under the math, you'll see function integral right above summation, number 9. Hit that, and notice on a TI-84 Plus, it gives you the look of how you wrote it down on paper. So you go 0 to 4 of x plus 4 dx, because you're taking the width with respect to x of all those rectangles, and what we get here is that is equal to 24. And again, be careful of units. It's not always unit squared. Right? I know it's area, and we're so programmed to saying area is unit squared, but in calculus, when we understand rates and different functions, it's not always a unit squared. So it's 24 and I'll just put some sort of units with a question mark. All right, it's about, that comes with the context of the problem. And if you want to see that as an approximation, so we can't use n to infinity, but let's say there was 20 rectangles. Let's approximate with 20 rectangles. I believe that's what your assignment does. So then we can do the sum from 0 to 19 of 4 over 20 of, and then the function of 0 plus 4 over 20x, which I'm just going to plug that in. That's 0 plus 4 over 20x. And if you put that in a calculator, let's see what happens here. So we get math, summation, and we're going from x equals 0 up to 19 of 4/20ths. And then the function, oh, sorry, this should be squared. And all of that's in parentheses. It's important when doing these, you write the parentheses properly on your paper and then transfer it in. More times than not, you make a mistake using parentheses. So then parentheses 0 plus 4 over 20x squared. And hopefully I did that right with that last parentheses. And notice that when you did that, we got 19.76, which is pretty far off from the exact error. So 20 rectangles, there was quite a bit of error, right? And notice that we used left endpoint. So this is a little bonus for those watching this video. This is left endpoint. And notice that when we use left endpoint versus the exact area, what did we get? We got a under approximation. And now we can see that. And the reason for that is because the curve was increasing. So what I wrote, f prime of x is 0, is just the same thing as saying f of x was increasing, which you could write that too. That's fine. I just like to be efficient. And there it is. Big thing from this video is knowing how to put down a calculator. You need to know how to do that on a calculator because that's how we get exact areas. Anytime we can be more exact in math, the better we are for it. All right. Hope that helps.